Hello everybody, and welcome back to another Big Ideas Algebra 2 lesson. Today, we're tackling section 7.2, which is graphing these rational functions that we've come to love so much. So, when it comes to graphing rational functions, we have to start with a parent function. As a reminder, the parent function of a graph is like the most basic version of a function. So like to make a straight line, for instance, a linear equation, the parent function is f of x equals x. To make a parabola, it's f of x equals x squared. And so on and so forth. The parent function for a rational function is f of x equals 1 divided by x. And the shape it makes is called a hyperbola. I listed off here that's almost like a star-shaped pattern. You could think of it as a star, you could think of it as like two curves, however you want to think of it. It's essentially going to be two branches that curl away from each other. Since these branches continue forever in each direction, the domain and range of a hyperbolic function is almost all real numbers. Almost. Let's see this in action. So here's what we're trying to do. We're trying to graph f of x equals 4 over x. How do we do it? Well, anytime you have a function that you don't know what it looks like, the best thing to do is to plug in for x. So for instance, if we plugged in 1 here, 4 over 1 is just 1. Or sorry, not 1, 4. So we know there's going to be a dot at 1, comma 4. With negative 1, it's going to be 4 over negative 1. That's negative 4. So negative 1, negative 4 is a point. As we go through and start figuring out all these points, we start to see a little bit of a pattern form. So in one direction, we're going from high numbers to low numbers. In the other direction, however, we're kind of going from low numbers to high numbers. It's essentially flipping over both the x and y axis. There's some symmetry here. So if we were to graph all of these, we can graph 2, 2, 3, 4 thirds. 4 thirds is just 1 1/3. And we can keep going on and on with the pattern, like 4 over 4 is 1, 4 over 5 is just 4/5, and so on. We can also continue in the negative direction, where 2, negative 2 is a point, 1, 4 thirds is a point, 4, negative 1 is a point, and so on and so forth. So we can continue this forever. The shape that we end up creating looks sort of like this. It curves in quadrant 1, and it also curves in quadrant 3 of our graph. We get these weird curves here. Now, it asks us to compare this to the to the parent function using our graphing calculators. So, to put in a fraction into a graphing calculator, we click alpha and then x. So if I did 1 over x, that's my parent function, and 4 over x, what do you think the difference is going to be? Let's find out. So here's our blue line, and there's our red line. It's almost as if we took the blue line and stretched it out. It turns out that this is, in fact, a vertical stretch. We would say that this is a vertical stretch of 1 over x, or f of x equals 1 over x. It turns out that all of our old rules will apply for this unit as well. Our rules about vertical stretches, shrinks, horizontal stretches, horizontal shrinks, all of it is the same. Now, notice how our graph goes through almost every single x and y value. Like if we look at the y values, we see that this graph is going to go up and up and up and up and up forever. we say this graph is going to go down and down and down and down forever. But there's one place where it's never going to touch. It's never going to touch our x-axis. It's going to get closer and closer and closer and closer, but never going to make it. The same thing with our y values. Or I should say, with our y-axis. It's never going to touch the y-axis either. It's just going to get closer and closer and closer. Let me give you an example. If I go into my calculator and I click zoom in, and I zoom in on right here where it looks like it almost crosses over. Let's see. It gets closer and closer and closer, but is never going to touch our x-axis. What we call these are asymptotes. An asymptote is a place that the graph is going to get close to, but never actually cross. Kind of cool. So this is how you graph the basic function 1 over x. However, we also know that we can transform these functions. So let's take a look at that. As we learned in Unit 1, and in Unit 2, and in Unit 4, if you know how to transform one type of function, you know how to transform all of them. It applies to all. I would like us to recall how transformations can affect the parent function. So over here on a separate sheet of paper, I'm going to personally make a table just so we can see this comparison. First off, what did we learn that vertical changes do? Vertical transformations. Remember that vertical transformations change the output, or the whole equation, and will go up or down in some way. Meanwhile, horizontal transformations change our input. So we're only changing our x. We learned this all the way back in Unit 1. But let's take a look at all these different types of transformations and see on here how it will actually affect our parent function. So, first off, we're starting with translations. As a reminder, translation is moving up or down. So, a vertical translation just means that we are moving our graph up and down by certain amounts. We're going to add or subtract from the output. So to the very end of our problem, in a way that it affects everything. Adding goes up, subtracting goes down. So let's go back to our graphing calculator. Let's say that I had 1 over x, and then at the very end of the problem, I did plus 2. According to what we know of transformations, this should move it up 2, right? Let's take a look. Here's our original in blue, and our red one is moved up 2 units. Perfect. Well, do you remember what horizontal translations are? It's the same thing. We're still adding or subtracting, but it's not from the output, it's from the input. So, instead of having the plus 2 at the end, what is our input here? Input is another way of saying our x variable. So if I add 2 to the x, how might this change things? Before we see the graph, remember that when you add or subtract from the input, adding is actually going to move it to the left, and subtracting is what moves it to the right. It's like the opposite. If we graph it, here's our original. Our new graph is 2 to the left since we added 2. Perfect! We can also do this with our transformations of reflection. So we can reflect over different axes in order to flip our equation. So, to reflect it vertically, that's a flip over the x-axis. A reflection over the x-axis means that we are going to make the output negative. And again, output means the whole thing. So, if we want to make the output negative, we're going to take our 1 over x, and what you could do is, you could put it in parentheses with a negative in front, or, remember that, with fractions, you could also have the negative right here. That makes the whole thing negative. Or, you could even have it on top of the fraction, right here. That's also the same as making the output negative. If I graph it, here's our original, here's our new version. Now we see where that star comparison comes from. Of course, if we want to flip it over the y-axis, or do a horizontal reflection, we make the input negative. Beautiful. Last but not least, we have our vertical and horizontal stretches and shrinks. And I want to remind you all that these ones are a little bit tricky. Let's start with vertical stretch. Vertical stretch means that you are multiplying the output by an a value bigger than 1. So basically multiplying it by a whole number, something that is bigger than 1. That's going to do a vertical stretch. Let's say we did 7 over x. It's multiplying our output, everything's being multiplied by 7, and it's bigger than 1. If we graph it, let's take a look at how it changes. There's our original, and this one looks like it's been pulled vertically. That's our vertical stretch. Again, keep in mind that when multiplying the output of these things, we could also do it like this. We could have 7 times 1 over... Oops, I wrote that incorrectly, I apologize. We could also write it as 7 times 1 over x. And it would still give us that vertical... Whoops. If you typed it incorrectly with a multiplication sign, like I was supposed to. This should also give us our vertical stretch. There it is again. Vertical shrinks are the same thing, except you're going to multiply the output by a fraction. Something that's in between 0 and 1. Now, this one is a little bit tougher to see how it happens. I want to remind you all of a couple rules about fractions. So, if we're starting with 1 over x, and we want to multiply it by 7, that'd be the same as multiplying the top by 7. However, if you wanted to divide 1 over x by 7, one rule of fractions is, when you multiply a fraction by a whole number, you're multiplying the tops. Dividing by 7 is the same as multiplying by 1 over 7, which means it's just going to multiply the 7 in the denominator. Aha! You'll see this written a couple of different ways. If you wanted to write multiplying by a fraction, you could write it with, for instance, a fraction times your entire parent function. That'll absolutely give us our horizontal shrink. In fact, it might be very hard to see. Yeah, you can see that it's barely there. We have to really zoom in order to see it. So there's our original in blue, and here's our shrunk version in red. You see how close it is? However, we could also just write this as, in fact, I'll write it on a new line so we can see it, 1 over 7x. And we'll see that that black line is the exact same as the red line. Just keep in mind that there are multiple ways you'll see it. In much the same way, horizontal stretches and shrinks are also multiplication, but instead of multiplying the output, we're multiplying our input by some a value. It flips around when you go horizontal. When you go horizontal, to horizontally stretch something, you're going to multiply it by a fraction. And to horizontally shrink something, you're going to multiply it by a whole number. So it's like the opposite of vertical. There we go. We're going to see more of these in action in just a little bit. Let's flip the page and see what we're talking about. So, we talked about the parent function 1 over x. But, much like how just x squared, like f of x equals x squared is the parent function for a quadratic, we can also write it in a form that makes it a little bit easier to transform. Like we learned about vertex form back in Unit 2. The parent function is still x squared, but we can transform it using a for stretches and shrinks and flips, h for left and right translation, k for up and down translation. It's the same thing here, it's just that instead we have our a on top, because that's what's multiplying the fraction, our h on the bottom, and our k here. As a reminder, a represents your vertical, stretch, shrink, and your flip. H represents your horizontal shift. And K represents your vertical shift. Here's a new rule, though. We kind of saw this a little bit on the graph, but I want to show you once again. If you shift horizontally, your vertical asymptote will also shift in that direction. If you shift vertically, your horizontal asymptote shifts in that direction as well. Let's do an example here. Let's say I added 5 to my equation here. That's a vertical shift. I'm moving up 5. So that horizontal asymptote, the place horizontally where it's not allowed to cross, is also going to go up 5. Oops, let me zoom out again, because we won't be able to see it on this graph. Oh, we can see a little bit, we can see a red line. But let's zoom out so we can see the whole thing. There's our original, and there is our red line. Our horizontal asymptote, y equals 0, moved up to y equals 5. So when you're graphing, you can tell where your asymptote is based on how things transformed. If I was to graph the equation, for instance, y equals 5, we'll see that that's the line that's never going to cross. Same thing for horizontal. If I shift this, instead of up 5, let's say I moved it right 5. Well, remember that moving something right 5 means I'll subtract 5 from the input. Our vertical asymptote is also going to move right 5. There it is. Very nice. At this point in time, I think we have enough information for us to try out some transformations. So, here's what we've got. On the left, we've got some problems where we have an original and then a transformed version. And you've got to describe in words what it is. On the right side, it's kind of the opposite. I'm describing in words what the transformation is, and you've got to write out the equation. I'd like you to try these out on your own, since we've done so many of these before in the past. What I'd like you to do is I would like you to try these 6, pause the video, and come back in a little bit. Hopefully you've had a chance to try these problems out. Let's see them done live. So, to find the transformations, we should first figure out what's different between the two equations. Our original f of x is just 3 over x. But in this one, it's 3 over x plus 2. We know that adding a k value shifts your graph up. So the transformation here is it's a translation up 2. It's a vertical translation. Let's look at the next one. Again, let's see if we can spot the difference. Well, the only difference is, it was originally 1 over x minus 3. Now it's negative 2 over x minus 3. So this negative 2 is the transformation. We've multiplied by negative 2. Since we multiplied the output by negative 2, we know there are going to be two transformations. The first is, since our output became negative, we know that's a reflection, a vertical reflection, over the x-axis. It basically flipped from top to bottom. We also know that since it's being multiplied by positive 2, this is a vertical stretch, because the output being multiplied by 2. For this one in particular, as well as some of the other ones on here, I want to graph them just so we can see the differences, because it's a little hard to tell sometimes when you're just looking at the equations. So, if I plug in, 1 over x minus 3 is my parent function, and my transformed version is negative 2 over x minus 3. That's plus. The transformation should be that it's reflected over the x-axis and vertically stretched by a factor of 2. It's kind of hard to see the stretch, but we can see it's absolutely flipped. In the next one, we again have to find out what's different, and in this one, there are 3 differences. First things first, our 4 got changed into an 8. That means that we must have multiplied our output by something. In fact, to go from 4 to 8, we know that's multiplying our output by 2. So it's a vertical stretch by a factor of 2. We also see that on the bottom here, we have 2x, 8 over 2x. So this is also going to be a horizontal shrink by 2. Last but not least, we have this negative 2 at the end. And since we're subtracting 2 from the end, this is a vertical translation down 2. That's it. Let's move on to the next one. For part D, if we want to vertically translate something down 7, what we're going to do is we're going to take our original f of x and subtract 7 from the output. So we are going to go f of x minus 7 is what we're looking for. So let's take another variable, g of x, to show that this is a different graph. And let's just change it where we have our parent function and then subtract 7 from the end. That's it. That's vertically translated down 7. Let's look at e. If we want to horizontally translate this 3 units to the right and flip it over the x-axis, there are 2 transformations at play. First things first, to move something to the right any amount, we are going to be subtracting it from our input. So we're going to change all of our x's into x minus 3's. And to flip over the x-axis, we make our output negative. So we turn the whole thing negative. That means g of x is going to be, instead of 5 over 3x, we'll make it negative 5. That's changing our whole thing. That's our flip. Over 3 times, instead of x, we're writing x minus 3. There we go. That's horizontally translated 3 right and flipped over the x-axis. This is another one that I want to just see live just so we can check our work. And you can always, 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 always check using your graphing calculator to make sure you've got these 100% correct. So, in my graphing calculator, I'm plugging these in. I'm plugging in 5 over 3x and negative 5 over 3 times x minus 3. So here's our parent function in the blue, and there is our transformed version. It moved to the right 3 and then flipped upside down. Love it! Last but not least, we have f, and there's a lot of transformations here. We're starting with f of x, and we need to vertically shift it 5 units up, flip it over the y-axis, then vertically stretch it by a factor of 4. To flip something over the y-axis, remember that that's moving it from right to left, it means we should flip our x to be negative x. To move 5 units up, we recall that's just adding 5 to the end. And to vertically stretch by a factor of 4, that's multiplying the entire thing by 4. The order does matter with these. Notice how I multiplied everything by 4. Because I multiplied everything by 4, this means we're first going to shift it 5 up and then do our flip. So the order does matter. This means that our function g of x is going to be first reflected with our x. So we're changing our x on the bottom into a negative x. So we've got our negative 3 over, instead of x, we're changing it to negative x. Whoops, sorry, I did it in the wrong order. That's okay. I should have said vertically shifted 5 up first, so adding the 5, then changing our x to negative, and then multiplying the entire thing by 4. The order does matter. So if I graph these two, we should see all 3 of those transformations. And I'll also show you what would happen if you did it in a different order, and how it would be a different answer. So there's our parent function, negative 3 over x. Our new function is going to be 4 times negative 3 over negative x plus 5. In fact, I might even just want to insert the multiplication symbol in here just to be safe, because I know we had a syntax error before. The alternative would be that we would just multiply our top by 4, right? The alternative would be that we write down negative 12 over negative x plus 5. Let's see the differences between the red and the black. The red is the correct one. The black is what happens if you didn't do it in the right order. So there's our parent function. There's our red one. There's our black one. Now I'd be saying, Mr. Strager, that is not a hyperbola. That is a red line. If I zoom out from the middle, we might be able to see it a little better. There's the hyperbola. There's what happens if you didn't do it correctly. The order does matter, so keep that in mind. All right. These are nice for rational functions that have this type of form. One thing over something else. However, we know that rational functions don't always look like this. In fact, in this unit, more often than not, we've seen rational functions that are crazy. Something like x squared minus 7x plus 12 over x plus 3, for instance. That's more like what we've seen, not a over x minus h plus k. So let's figure out how to graph these. So, believe it or not, we've already made good progress towards figuring out how to graph these. In section 7.3, we started talking about restrictions, things that our x is not allowed to be. It turns out that the vertical asymptote of your graph, the place where your graph is never allowed to cross, is just your restrictions, or values that make your denominator equal to 0. So once we solve these equations and get our restrictions, we know where our graph is not allowed to cross on the vertical axis. The horizontal asymptote is a little bit different. Your horizontal asymptote can be found by dividing the leading coefficients of the numerator and your denominator. Let me give you an example. Let's say I gave you 6x plus 6 divided by, whoops, we can't see that. 6x plus 6 divided by 2x plus 2. We can see what the leading coefficients are. It's 6 and 2. 6 divided by 2 is 3. So we know that our horizontal asymptote, the place where we're not allowed to cross horizontally, is going to be x equals 3. To find the vertical asymptote, we just need to find our restriction. So we solve the problem like we do normally. See what we can take out from both groups. Make any cancellations you need. 6 over 2 is just 3, but our restriction is that x is not allowed to be negative 1, right? That's your vertical asymptote. Your vertical asymptote, I'll call it the vertical A, is going to be y equals negative 1. So this is what we can do to transform what we already know into graphing. Here's something I should mention. Whoops, I realized I did this. I'm sorry, y'all. This example was done incorrectly. It was for a different purpose. I apologize. It wouldn't be your vertical asymptote. Your vertical asymptote is just whatever makes your denominators 0. So for instance, in this equation, it'd be negative 3. In this equation, we'll have to take a look. But something to note is, if something cancels, which is what I was trying to show here, in the numerator and denominator, your graph will have a blank spot at the x value where that cancellation occurs. It's literally just going to be a spot on the graph that doesn't exist. It'll be just empty. This is called a removable discontinuity. And we draw these as an open circle breaking a branch. So here's how to graph a rational function. Figure out your asymptotes and draw them. Then plot at least 2 other points. I usually go for 3, but plot a couple of points on either side of your asymptotes. Then draw the branches of the hyperbola through those points. Let's do a couple examples together so we can see this in practice. So, example 3 is asking us to graph the following, then list the domain and the range. So let's start off by talking about our asymptotes. Remember, your asymptotes are going to be whatever your leading coefficients are will be your horizontal asymptote. Whatever you get as your restriction, or whatever x is not allowed to be in the denominator, that'll be your vertical. Okay, well if we take a look at this, the leading coefficients here are 1 and 1. Since 1 divided by 1 is just 1, we happen to know now what our horizontal asymptote is. Or sorry, our vertical asymptote is. Horizontal, I mixed up once again. A horizontal asymptote tells us we cannot have any points at 1. So horizontally, we cannot cross 1. This is our asymptote. However, also keep in mind that here, 1 would also make the denominator 0. So our vertical asymptote is 1. What we would need to do next is we would need to figure out a couple of points on either side of these asymptotes. So like plugging in 1 for x wouldn't work, but let's find a couple of x values that we could plug in. For instance, 2 is to the right of our asymptote here, so let's plug in x equals 2 and see what we get. 2 plus 5 is 7. 2 minus 1 is just 1. Or sorry, 2 minus 1 is just 1. 7 over 1 is just 7. So that means you're going to have a dot all the way up at 1, 2, 3, 4, 5, 6, 7. Ooh, I'm glad that I made this graph as big as I did. Another point we could try is 3. So if we plug in 3 here, 3 plus 5 is 8, divided by 3 minus 1, which is 2. 8 divided by 2 is 4. So we know that at x equals 3, our graph is going to be at 4. If at this point you want to add in another point, just to make sure you've got it in the right spot, you can. We could do 4, for instance. Like if I did 4 here. 4 plus 5 is 9. 4 minus 1 is going to be 3. So 9 divided by 3 is just 3. And we can start to see what this branch is going to look like. So we can just draw this branch right here, and we know that it approaches the asymptote but never touches. Beautiful. Of course, we want to have another branch on this side, so we should pick some negative numbers that would work, or anywhere as long as it's to the left of this asymptote. To the left of this asymptote is 0. So what would happen if we plugged in 0? That'd be a cool number to plug in. 0 plus 5 is 5. 0 minus 1 is negative 1. And 5 divided by negative 1 is negative 5. So 0, negative 5 works. Okay, we can keep on going and find more numbers to plug in. Of course, you want to plug in something that would be nice to plug in. Negative 1 would be another one that's nice to plug in, because negative 1 plus 5 is 4. Negative 1 minus 1 is negative 2. 4 divided by negative 2 is just negative 2. So negative 1, negative 2 is a point. And I'm going to plug in one more for good luck, but again, you only really need 2 points. If we plug in negative 2, which also works out very nicely, negative 2 plus 5 is 3. Negative 2 minus 1 is negative 3. 3 over negative 3 is negative 1. So 2, negative 1, or sorry, negative 2, negative 1, I should say, also a point. And we can graph our hyperbola. Very nice. For the next one, we can do the exact same thing. So, to find our horizontal asymptote, we know that we have to do our leading coefficients 2 divided by 1. Keep in mind that in factored form, it's a little bit difficult to see what the leading coefficients are. You might have to actually multiply these out to find what your leading coefficient is. In this case, though, 2 times x is 2x squared. That'll be the top leading coefficient. The bottom leading coefficient, x times x, is just 1x squared. It's 2 over 1, or 2. So our horizontal asymptote is 2. Beautiful. But what about our vertical asymptote? Well, here's our horizontal at 2. For our vertical asymptote, we should ask ourselves, what would make the denominator 0? There are 2 answers. In this case, we see that 2 and negative 3 would work to make the denominator 0. But remember what I said. On the last page of the notes, I said that if something cancels out, it's called a removable discontinuity, and it would just be an open circle at that place. Does something cancel out here? And the answer is yes. X minus 2 and x minus 2 cancel out. So we would have a vertical asymptote at just negative 3. So at y equals negative 3. There's our vertical asymptote. However, we wouldn't have an asymptote at 2. We wouldn't draw another line. We would have what we call a hole, or removable discontinuity. The removable discontinuity at 2 means that we should have a hole where x equals 2. When we graph it, it just means that we'll graph anything that goes through x equals 2 as an open circle. So let's see if we can start putting together a table. What I'd like you to do is I'd like you to pause the video and pick a couple of numbers that are to the left of our vertical asymptote for x, to the right of our vertical asymptote for y, or for x. Plug them in and see if you can make the graph here. Just make sure you have an eraser on hand, because we might have to do some erasing here as well. Pause the video and try it out. Alright, so some numbers that might work nicely here would be as follows. We could, for instance, plug in numbers like negative 4. I mean, negative 4 is right up next to our vertical asymptote. If we plug in negative 4, we might have to do a little bit of math to figure out what the y value is going to be. So let me grab my handy dandy paper here. Let's see what happens when we plug in x equals negative 4. 2 times negative 4 minus 2 times negative 4 plus 1 divided by negative 4 times, minus 2 times negative 4 plus 3. This will give us 2 times, this is negative 6, negative 6. This is negative 3. So 2 times negative 6 times negative 3 divided by negative 6 times negative 12. When we do the math here, we get that this is going to give us negative 6 times negative 3 times 2 is 36. Whoops, I'm sorry, this wouldn't be negative 12, this would be 1. Negative 1. Negative 6 times negative 1 is just 6. This just gives us the answer of 6. See, even math teachers can get their math wrong sometimes. This gives us a y value of 6. So at negative 4, we see that we're going to have a y value all the way up at 6. So we plot our point right here. Beautiful. We could also try, for instance, negative 5, so 1 over. If you did it much the same way, if you do it in much the same way, you would find that we would get 4, according to my calculations. So it'd be right here. This means that our hyperbola is going to have an arm that goes like this, and an arm that's going to be down here. It's not what you expect. For this next one, we can plug in a couple of other digits and see what works. Remember, it's anything that's to the right of this line here. So, for instance, I could plug in negative 2. When you plug in negative 2 for all these x's and solve, we should get negative 2. So we could put a dot here at negative 2, negative 2. If I was to plug in negative 1, for instance, it turns out plugging in negative 1 actually gives us 0. So we would get a dot here at negative 1, comma 0. And you could put more points on this line if you would like, but we don't need to. We can graph it here. The only thing I'd like to mention is there is going to be what I mentioned as a hole at x equals 2. Like, for instance, I'll tell you that this is going to be 1, 1. I'll tell you that when we plug in the number 3, we get 4/3, so like 1 1/2, or 1 1/2, 1 1/3. When we make our branch, we want to make sure that we leave a big empty space at x equals 2. To do that, we put a circle there, and we make sure that it cuts right through the middle of our hyperbola's branch. That is how you would make a hole. You would literally draw a circle at that place on your branch. Last but not least, I'd like you to try out C. Pause the video and try out C and check your answer. How'd you do? This one's a little bit unique because a lot of the answers we get are going to be decimals or fractions. It's okay, you can approximate for these graphs. We're not looking for perfection with these. What we're looking for is the asymptotes. We're looking for any places where there is a hole. And we're looking for the graph to be in the right direction. All right. Last but not least, we see that one of these forms is much easier to use than the other. So, if we want to go from one form to another, we should know how to switch it up. This is how we can switch from this more complex form to our more simple form. It's much easier to graph a simple rational function. So here's how we do it. Recall that a complex fraction like this is just saying the top of it divided by the bottom of it. If we can actually go through and divide our numerator by our denominator, we might end up with a quotient and a denominator that looks a little bit more like this. This is where we're going to have to use either synthetic division or long division. Yes, we are going back to that. I told you it wouldn't disappear. So, let's take a look at 4a and see if we can do it together. So, it says using division to rewrite the following functions in this form and graph the result. Recall that when we divide, we're going to end up with a polynomial and then a remainder. But doesn't your remainder normally look like a over x minus h? K stands for our polynomial, and a over x minus h is our remainder. So let's take a look. If we want to set this up, we can use synthetic division because we're dividing by x plus 1. If it's x plus something or x minus something, we can do synthetic. If not, you might have to use long division. In synthetic division, the number we put up here is going to be whatever that h value is, -1. And here our coefficients are 3 and 5. So let's do it. We bring down the 3, multiply by -1 to get -3. 5 minus 3 is 2. So what we end up with is 3 with a remainder of 2 over x plus 1, right? What this is saying is we can graph this as f of x equals 3 plus 2 over x plus 1, and this is just a transformed version of one of our graphs. This transformed version is just telling us that it's going to be to the left 1, and it's going to be up 3. Nothing too crazy from what we've already seen before. So we have just learned how to transform from the more complex form into something that's a little bit more easily graphable. So, since our denominator cannot be -1, we know that that's going to be our asymptote over here. So that there is our asymptote. And since our leading coefficients are 3 and 1, 3 divided by 1 is just 3, we also know that our asymptote on the y-axis is going to be right there. Now we just do what we always do. Pick a couple of points and graph. I've already taken the liberty of plugging in a couple of points, a couple of them to the left of -1 and a couple of them to the right of x equals -1. So let me plot those points down for you real quick. We would get -2, 1. We would get -3, 2. And those are the only points we really need in order to graph this. As a reminder, there's no hole because nothing looks like it's going to cancel out here. In some later problems, you might have to check. And over on the right side, if you plug in 0, you get 5. So right up here. If you plug in 1, you get 4. So we can graph this branch like this. Done. Try and see if you can use synthetic division in order to plot the others here. Pause the video and see what you can do to use synthetic division and solve. Alright, just to demonstrate the synthetic division one more time, if we wanted to do synthetic division here, we know that 2 times -1 is -2. 1 is our remainder. We would end up with 2 plus 1 over x plus 1. Once again, this we write as a function. And from here, we just do the transformations. Plus 2 means up 2. Plus 1 near the x means left 1. So our asymptotes are also going to be moved up 2 and left 1. And we can check that by finding the leading coefficient and what our denominator is not allowed to be. Essentially, we get our asymptote has moved to the left 1, our other asymptote has moved up 2, and we can graph it as normal. In this case, again, I'll just tell you a couple of the points, but normally you'd have to plug these in. I'll tell you that at 0, our function has a value of 3. At 1, our function has a value of 2.5. So we can already plot this arm. We know it's going to be relatively close to our asymptote. Perfect. We know that at -2, it's going to give us a value of 1. We know that in order to get -3, it's going to be like 1.5, so it's going to get even closer. So this is going to be our asymptote here. And again, you find these out by plugging in values for x into either this equation or this equation. In fact, this equation might be a little easier to plug into. Last but not least, for part C, we can once again divide these two. This time we're synthetically dividing by 2. So, we bring down the -5. 2 times -5 is -10. So that's -4. With the remainder of -4, we would write this as -5 minus 4 over x minus 2. That's our function. So again, we see that our asymptote here has moved down 5, and this asymptote here has moved to the right 2. Bam, 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 bam. And this one is going to be down 5. In this particular case, it's going to be a little bit weirder to find different points. Usually the bigger the numbers, the stranger the points are, but we are still allowed to set this up and plug in for x. Some values that I happen to find for this one are that at 0, we have a value of -3. At 1, we have a value of -1, right there. So it seems to go in this direction. And that kind of makes sense. We have a negative here. We know that in this form, the negative top number means that it's going to be flipped. It's going to be a little bit trickier to graph these other values here for like 3 and 4. But at 3, we get a value of -9, which is a little bit off our graph. And at 4, we get a value of -7, which is a little bit on our graph. We have this branch. Beautiful. So this is how we transform and graph hyperbolas. Thank you so much for listening, everybody. I hope you have a terrific rest of your day.